1.1, our first lesson in pre-calculus, is about functions. We're going to do a nice review of functions. And your essential question is, how do you work with functions that are represented verbally, graphically, algebraically, and numerically? You have seen functions in all of these representations. There's really nothing new here, just a nice review. I'm going to go over each one of these terms individually, and you'll definitely recognize them. So I'm going to start with a problem that I took out of your book. It's about a cup of coffee. And verbally, you guys like to think of these verbal representations as the word problem. So that's what verbally means. It's the words or the reading it out loud. So verbally. And we have this problem about a cup of coffee, which I'll get to in a minute. Let's look at the other representations, however. Below the word problem, you also have the graph of the problem or of the function. So that is the graphical representation. To the right of that, you have a table of input and output values. The table of values, we call that the numerical representation of the function. And to the right of that, you actually have the equation of this function. So the algebraic representation of the function. So truly nothing new there for you. All right, now let's go through this problem, and as we go through this problem, I'm going to also be talking about some other vocabulary, again, just a review. If you pour a cup of coffee, it cools more rapidly at first, then less rapidly, finally approaching room temperature. And if I look down at the graph, I see a curve that is decreasing pretty rapidly and then decreasing less and less rapidly as we move on to the right. Now the temperature Y, which tells me that the temperature is going to be along the y-axis, and I can see that here. My vertical axis or my y-axis is in degrees Celsius. And that is a function of time, x, which I can see along the x-axis, and the time is in minutes. Now, saying that the temperature y is a function of time means that the temperature is dependent on the time. So we're going to come down here and we're going to define what it means to be a dependent variable versus an independent variable. So our independent variable here is like our inputs, and our dependent variable is always dependent on those inputs. And because usually when we're dealing with functions, we think about inputs before we think about outputs, I'm going to define the independent variable first. So again, the independent variable, well, these are really just your inputs. And like in a table, if we were representing a function numerically, we would choose our inputs, plug them into the function, and get our outputs out. Okay, so I'm going to start with inputs. So our independent variable, another fancy way of saying that, that's our input. It is represented with the values along the x-axis. That's another reason why I'm starting with independent variable, because when we graph points, we usually go along that x-axis first. However, we're not just going to think of this as the x-axis because it doesn't always have an x representing it. In this situation, it does. And in this situation, it represents minutes. But let's also just call this the horizontal axis, because we may use other variables to represent it. And if I think of all the independent variables that could possibly be represented by a function, that entire set is called the domain. So the domain is the set of all possible values for the independent variable. Okay, so let's move over to our dependent variable. And again, our dependent variable is dependent on our independent variable. So yeah, choose an input, you plug it in, you evaluate the function, you get out your dependent variable, or what we like to call our output. So a fancy term here is outputs. Now, usually we like to think of our outputs along the y-axis, but again, we won't always use the y variable. So you want to also think of this as our vertical axis. They are represented along our vertical axis. And in this situation, our vertical axis is in degrees Celsius. So our outputs here are the temperatures in degrees Celsius of the cup of coffee. And if we think of the entire set of all the possible outputs, that's going to be range. So our range is the set of all possible values for the independent variable. So let's go ahead and let's identify our domain and range for this problem. So the domain, again, is going to be all the inputs along that x-axis. It looks like we're starting at time being 0 minutes. And at time being 0 minutes, I can look at my table of values and see that the degrees of the coffee, of the cup of coffee, was 90 degrees Celsius. And that's actually going to be the y-intercept of this function. We'll talk more about that in a minute. So I can see that the very minimum value of my domain is 0. And then moving towards the right, well, on this graph, it's 30 minutes, but could that cup of coffee sit there even longer? It could. There's not an arrow at the end of this graph, so you could potentially identify this as our domain being between 0 and 30, or you can just say that x can be greater than or equal to 0. Okay, and then our range, well, the hottest that this cup of coffee will ever be is going to be 90 degrees Celsius. After that, like the problem said, the temperature of the coffee decreases very rapidly until it starts to decrease less and less and less rapidly. So maybe, what is this, like at 8 minutes? Put a little dot there. At 8 minutes, I can see, okay, now it's starting to decrease less and less and less, and it's approaching the temperature of the room. It's getting closer and closer and closer to the temperature of the room. So actually, the temperature of the room then is going to be our lowest bound for our range, and that's actually our horizontal asymptote. And we can actually write an equation of that line. So it's at y equals 20 degrees. So I would say that my range is between, well, the highest it's ever going to be is 90 degrees. So it's definitely going to be less than or equal to 90 degrees. However, can it ever actually be 20 degrees? Well, not according to what I'm seeing here. It looks like it's just going to get closer and closer and closer to 20 degrees, but it's never actually going to reach. So until it is so close to room temperature, but nobody ever said it actually got down to 20 degrees. So I'm going to put here that y can be greater than 20 degrees, but not equal to. Which brings us to our next vocabulary word here, which is an asymptote. Now, we saw a lot of asymptotes last year. So I've just pulled out my parent functions, which hopefully you have, and if you do, you should also pull those out. So on this first page, I don't see any asymptotes. Moving on to the next page, let's see, I've got logarithmic and exponential functions, and both of those had asymptotes. Now your exponential function has the horizontal asymptote, whereas the logarithmic function has the vertical asymptote. And at the bottom here, the rational function actually has both. It's got a vertical asymptote and a horizontal asymptote. And later on this year, we're going to learn that it also can have other types of asymptotes, which we call these oblique asymptotes. So let's define asymptote. And we'll define it in terms of what we know about asymptotes right now. Later on, it's going to get a little bit more complicated. But right now, we know that asymptotes, or an asymptote, is a line, a graph, gets arbitrarily close to, but never touches. And what does this arbitrarily close to mean? Well, this just means as close as you want. So looking back at this graph, I can get as close to this line as I want. So as I move further and further and further to the right, so at maybe, 30 minutes, it's like 20.0001 degrees Celsius, right? And maybe at, 20 minutes, it was 20.1 degrees Celsius, right? So I'm getting closer and closer and closer as I approach, or as my time increases, I'm getting closer and closer and closer to that 20 degrees Celsius temperature. I'm never actually getting exactly to it, but I can get as close as I want. I can, again, get, 0.0000. I could do this all day long to get as close as I want. This is really going to come in handy as we move forward and get into calculus. We're going to explore this concept called limits, and these asymptotes help us determine some of our limits of functions. So now I have a challenge for you. What kind of function are we talking about? So let's go back to our parent graphs. All right, well, we already determined that none of these even had asymptotes, so it can't be any of these functions on our first page. Moving on to the next page, we said that there were two that had asymptotes, either exponential or logarithmic. And the exponential were the only ones with the horizontal asymptotes. And in fact, this exponential function looks a lot like my decay exponential function parent graph. Is it an exponential function with a decay? Well, let's talk about that. So does it follow the parent function form? So does it look like one of these two functions? And if it's a decay, then we know that the base of the exponential piece of the function, right, so our b here, has to be something in between 0 and 1. All right, let's look back at our function. All right, looking at our function, I can see that my b is 0.8. So this right here, this is my b. Right? The base is being raised to a variable, or to my input, or to my independent variable x. All right, and yes, b is 0.8, so it's definitely between 0 and 1. Which tells me that this actually is exponential decay. All right, so what's the 70? Well, the 70 is your vertical dilation factor, right? So this is like your A, and that's vertical dilation. Okay, so this thing is stretched vertically. And then you've got your plus K, or your 20, which is your vertical translation. So this part is our vertical translation. which is up 20, which is how we got our horizontal asymptote, right? We took that parent graph and we shifted it up, all right? And if you need a note about this being your vertical dilation. So this, in fact, is an exponential function. It's actually an exponential decay. So in this lesson, as you start to look at some of these graphs, at some of these functions, be looking at your parent graphs too and asking yourself, hey, what kind of function is this? What are some characteristics of this function? And the last characteristic of the function that we'll talk about is, again, that y-intercept that I promised to go back to. So this here, that's your y-intercept. And you can also see that y-intercept right here in your input-output table. So when you plug 0 in, you get out 90. And that's always a great way to find your initial value, or in this situation, the temperature of the coffee when it was first poured. And I can also use my function to find that y-intercept. So if I took my function and I plugged 0 in here for x, well, 0.8 raised to the 0 power, that's going to be 1. And 70 times 1 is 70 plus 20, you get your 90. So in our next class session, we will work on the comparing two cars given distance. I'll introduce you to a couple new vocabulary terms, and then we'll answer these questions. And then before I let you go in this video, I'd like to go over what mathematical modeling is. And the entire reason why math even exists is because people were curious about the world around them, and they wanted a way to explain the world around them. And that's basically what mathematical modeling is. What people do is they observe data over time, and they take that data and they run regression analysis on it. You'll learn more about that later. And they come up with a function that best represents that set of data. And then they use that function to analyze or predict and explain what's happening around us. So I gave us a list of just a few things that I could think of, but there are many more ways in which mathematical modeling are used. Some things that I thought of was epidemiology. That's the study of epidemics. So that's people using both math and health data to track the spread of disease and viruses. I actually included here a graph of the growth of the Ebola virus in the United States in 2014. You can see that it's following the model of an exponential growth function. I also included a graph of hydrology, so predicting water flows like in the Eel River at Fernbridge. We pay really close attention to this pretty much every winter, right? We're wondering, hey, is the Eel River going to flood at Fernbridge? Now notice the graph here. This looks a lot like the shape of possibly a parabola. Okay, so they could potentially create a function modeling a parabola that would give you a pretty good idea of where the river would be at a certain time within, these few days that they've mapped out. Weather, predicting weather patterns. How do you think that your weather app works on your cell phone? Functions. Okay, finance, assessing the risk of certain investments for businesses as well as for individuals. Also looking at investment strategies. Urban planning, where is traffic? How can we better build our infrastructure to alleviate some of that traffic or to make it easier for people to get around town? Sports, I think that they use data and modeling to definitely pick their teams and then to forecast who's going to win. And then space exploration was another one, right? Sending rockets and shuttles into space, but also satellites and even the engineering behind satellites. All right, and then we'll create another video for us to finish the rest of these examples in the notes, and we'll do another exploration. This exploration, we'll do this in class as well.